Welcome to Physics 2 Lab 6, Faraday's Law. Here is an introduction to this lab. The purpose of this lab was to study induced/eddy currents by analyzing observational data where we drop a bar magnet through an aluminum tube and data gained analytically from a computer simulation using GlowScript. The system in this experiment is the bar magnet and the aluminum tube, while the surroundings include everything else. From our results, we found that the observational data, it took an average of 1.24 seconds for the strong bar magnet to fall through the aluminum tube. In our computational model, it took an average of 0.783 seconds for the bar magnet to move through the aluminum tube. Here are the fundamental concepts for this lab. The first fundamental concept is Faraday's law. This law states that a changing magnetic field through a loop causes a magnetic flux which can induce a current in the loop. The second fundamental concept is Lenz's law. Lenz's law, represented by the negative sign in Faraday's law, demonstrates that the induced current in the loop opposes the change in flux that induced the current in the first place. The third fundamental concept, which we used in the computational model in order to update the position of the bar magnet, was Biot-Savart's law. This demonstrates that a moving particle/current can produce a magnetic field which depends on the distance and strength of the current. Here was a procedure to our lab. First, we collected our observational data. We did this by dropping a strong bar magnet through an aluminum foil tube. Dropping the magnet through the aluminum tube causes a change in magnetic flux, inducing an opposing current in the tube that slows the travel of the magnet through the tube. We recorded the time it took for the magnet to drop through the tube. That was our observational data. Then, to collect our computational data, we simulated the drop of the magnet through the tube using the GlowScript code and compared the average times required for the magnet to drop through the aluminum foil. Here is our observational data over 5 trials. There is the start, stop, and elapsed time. The average time taken for the magnet to move through the magnetic tube was 1.23 seconds. The code to the left represents the functions that we use to calculate the magnetic field of the bar magnet and the function that we use to calculate the magnetic flux. The code to the right represents the while loop, which we use to update the position of the magnet using the position and velocity update formulas. We do this by adding up all the forces acting on the bar magnet. Here is a visualization of the bar magnet falling through the aluminum tube. The initial steep slope represents the range where the force due to gravity is greater than the force due to the magnetic force. The part of the graph that is flat represents the range where the force due to gravity equals the magnetic force. Finally, the graph goes back to rapidly dropping in the final few seconds where the force due to gravity is greater than the magnetic force. Here are some errors and assumptions that we made during the lab. First of all, there was errors with the time measurements. There's a good possibility that we did not precisely stop and start the stopwatch. Next, we assumed there was no air resistance. Because we did not consider the effects of air resistance when we were modeling the magnet falling through the tube using the GlowScript code, there could have been differences in the average time. Finally, we also did not consider the effects of friction as the bar magnet falls through the tube, which could have made the magnet fall slower. What if questions? What if the resistivity of the conductor were reduced as close to possible to zero? According to Ohm's law, decreasing the resistivity would increase the strength of the opposing induced current in the tube. This would result in the bar magnet moving very slowly through the aluminum tube. What if holes or slots were cut into the tube? There would be much less rings of current through the tube. This would result in a much weaker opposing magnetic field caused by the bar magnet to move through the tube at a much faster rate. In conclusion, this experiment helped us understand why a bar magnet moves through an aluminum foil tube at a much slower pace. We were able to apply the concepts of Faraday's law and Lenz's law to explain the observations that we made during our lab.